Okay, I'm hoping to have exams to get back tomorrow. That is the goal. We'll see if it happens. As far as I know, the process has at least started.
If we're not gonna be here tomorrow, can we still go into your office
Yeah.
and look at them?
Yeah, for those of you who aren't aware, I do collect exams after we go over them again, but then I store them in my office at least until you graduate, plus a year or two. So you're always welcome to come take a look at them in my office, but I don't give them back, and that's what allows me to not have exams leak. I've had issues with that in the past, basically, and that way it feels like every time I give an exam, I have to rework every single problem and not just, change the numbers, but change the exact subset of change every question significantly and not reuse a concept or an idea for years. That's annoying. All right, so nothing really hugely upcoming for announcements. We have an assignment due next Wednesday. I have not yet gotten out the next assignment, but I will probably get that out sometime relatively soon. I don't yet know if it'll be due the following Wednesday or the Wednesday after that yet. I'll have to make an executive decision based on the rate at which we're covering content in class and just thinking through the rest of the quarter, what we want to make sure we've covered for exam 2. Yeah,
I had a question about the CYK algorithm
Yeah.
assignment. So when I was reading it, it was saying that we only have to do one of the 2 programming assignments at unit assignments.
that's probably old language. I should have read that before I read everything before I revealed it. I am trying to make sure that I pace the class so that we can get both of them done this time.
Oh, okay. Yeah, just
Historically, we've been covering the LL parsing the end of the week before the final week or the start of that final week. So it would be, we're going over the content. You have a project due in two or 3 days with regards to it. So historically, I've said, do one of the 2 and do a second, you get extra credit. I may still end up doing that this quarter, but I would like to, I really want people to have reason to do both projects because I think it's really informative to get that work done. I think we will see, but for now, assume that you're going to be doing 2 projects, and I may roll that back. Questions before we dive back into non-deterministic push-down automata? In we go. So we did this example at the end of class. Last time we drew out a solution to this that involved a 3-state solution with 6 transitions on that middle state, all manipulating the stack characters, as well as some of them looking for, I guess all of them were looking for characters from the input. But we found that when we transitioned from the initial state to the middle state, that all we were doing was adding the bottom of stack character. When we transitioned from the middle state to the end state, all we did was remove that bottom of stack character. And neither of those involved reading characters from the input string, which was something that was new, at least to this idea. We saw that with lambda transitions, but now the lambda is only half of the transition. We can make no change to the input, but also manipulate the stack and vice versa. We can also do that. So we ended up getting something that looks kind of like this. This solution assumes that the bottom of stack character starts on the stack. And again, if you make any assumption with that, just state the assumption about what that is, and I can easily figure out what assumptions that you made based on that. I can still determine whether your solution is correct.
Doesn't it end with the bottom stack character too? Because it's got the CC.
Yeah, it does.
Yeah.
It does accept from the bottom of stack character being on. So those are 2 assumptions that I am okay with, especially because the book is a little bit wishy-washy on which one is there or not. You're supposed to accept an empty stack, but how do you define an empty stack? Do you define an empty stack as there's nothing on the stack, or an empty stack where the bottom of stack character is on the stack, signaling that you have an empty stack? There's no right answer to that, really. So whatever you choose to do with that, just be consistent. So let's look at, we talked about instantaneous description. Do we remember what the three components of the instantaneous description were, just so we can do that? Yeah.
Input string, stack character, and then whatever you're pushing.
So, yeah, that was the transition triple, I think, for what these triples are here. But if we're looking at the instantaneous description, for something like, how does this produce BAAB? There was a triple that defined that instantaneous description with three components.
Is it a state of control unit, unread portion of the string, stack contents?
Yep. So you can do something like, we're gonna use the turnstile symbol. So here would be the first instantaneous description. We start in state Q0. The unread portion of the string is BAAB. We have not yet read anything. And the stack contents is just Z. The bottom of stack character is the only thing that is on the stack when we begin. So this turnstile symbol now says that moving from here, we can take some transition, and that's going to change the state that we are in, potentially, the amount of the string that's been read, and the stack contents. So what would, if we were trying to determine whether BAAB can be read from this NPDA, what would the next instantaneous description read?
What was the second component again?
The amount of the string that we have yet to parse, or yet to read.
UF, empty string.
So with a single transition, we should be able to do this with a single transition, and we could make a transition to QF. But if we're trying to accept BAAB, then we need to read that first B as the next thing that we do. So we'd be looking for some transition that reads a B.
So it'd be Q0, AAB, Q0, or 1Z.
Yeah. Yeah, so if we take this transition defined right here as one of these 6 transitions, then we would go from Q0 to Q0. So the first part of the new instantaneous description would still say Q0 as the state that we arrive in. AAB would be the second part, because to do this transition, we had to read a B, which was the first component from this string. And then the stack contents, when you do this, says pop a Z, push the Z, and then a 1. So the stack contents would be reading from top to bottom, 1Z. So that's what we're gonna see in the next instantaneous description. We're still in Q0. We've read that first B. What remains is the AAB, and the stack contents from top to bottom are 1Z. What's the next transition that we would want to make in order to determine if we can accept BAAB?
It'd be Q0, AB, and then lambda.
Q0, AB, and then since this lambda, we're saying we're reading an A, there is a 1 on the stack. So we're gonna pop that 1. So that what's remaining on the stack should just be the Z. This basically says pop that 1, it's gonna get rid of the 1 that's on top of the stack. So what remains is just that bottom of stack character. But other than that, absolutely perfect. So Q0, we've read that A, what remains is AB, and the bottom of stack character is the only thing on the stack. What do we do next?
Push to 0.
Push to 0. So what's the transition going to be? Which one are we using?
The second one on the far left.
This one. We read an A, bottom of stack character is a Z, so we can push a 0. So we're going to stay in Q0. We'll have read the A, so all that's left is a B, and the stack should read as 0Z. Since we pushed that 0 onto the stack. So there's still something to read here, that last B. How do we do it? Which transition are we using?
Far right. Middle one.
If we read a B and there's a 0 on top of the stack, we can just pop the 0, transition from Q0 to Q0. So this tells us now that the string, what's remaining in the string is empty. So we just refer to that as lambda. So we're in state Q0. There is nothing left to read in the input string. And all we have is the bottom of stack character. So this tells us that we can now take this transition to our final state, because we're making no change to the input string, popping a Z and optionally pushing that Z back onto the stack, depending on how you want to do this. It's okay if this is a lambda, it's okay if this is a Z, doesn't really matter to me. But that says that we can transition to QF. So the final instantaneous description says that we're in QF. There's still nothing left to read in the string, and there's a Z on the stack according to this. It's also okay if that is lambda. But it will only be okay if that is lambda if this character here is also lambda. So that's an example of instantaneous descriptions, and you just use that turnstile symbol between each of those instantaneous descriptions that says we can get from this state to this state via some transition in the transition graph. It doesn't tell you which transition you are using, it just says it is possible to get from this instantaneous description to this instantaneous description via a single transition in the NPDA.
So would you condense this down to like the first and last ones to say?
You can, if you put a star over this turnstile, it says that we can get from here to here via 0 or more transitions. So if the question says, what is the process? How can you show that it is? Then you want to go through each of those steps. But if, on the other hand, you just want to be able to say it is possible to get from here to there and you don't have to show it, then you would just state kind of the star closure of the turnstile symbol. Via 0 or more transitions, we can get from this instantaneous description to that instantaneous description.
Can you say what the last element is in the instantaneous description?
This element,
Yeah.
oh, you're saying which one? This is the stack contents?
Yeah.
Yeah, stack contents from top on the left to bottom on the right. Any questions on that? Feel like we could reproduce that on a homework if need be? All right, let's try another example. Here's a language. Another one that we have shown via pumping lemma to not be regular. Can we make an NPDA to accept WWR, a string followed by that same string in reverse, even length palindromes? To nudge you in the right direction, don't think about making an NPDA from the very beginning, think algorithmically. Since this is a non-deterministic pushdown automata, we can utilize non-determinism. So imagine that you're reading a string from left to right and you're trying to map it to WWR. Allowing for non-determinism, what do you do?
Push W onto the stack, character by character, and then you pop each character off the stack for WR. And
Right.
if it's up to you.
How do we know we have transitioned from W to WR? Because now we don't know, since we're reading, we don't know what that length is to be able to say when we reach that halfway point. So that's where non-determinism is going to help us. We can branch and say, on one branch, we're going to assume that this is the last character of the first half. And on the second branch, we're going to say, we're going to assume that at least one more character to come is still part of that first half. So if you follow that branch for every single character, you would eventually be able to say if one of those threads returns yes, then it's WWR. Does that make sense? So how would we construct that as an NPDA? You know, the one headache in this is removed by this being a plus and not a star. So we do not need to accept the empty string. This is to the number of states that we want. So we know the transition out of the first state adds the bottom of stack character, and the transition out of the last state removes the bottom of stack character. There are 2 states just for that. How many total states? That's the right answer. A 4-state solution. What is the second state? What is the purpose of that second state?
Maybe, W.
Yeah, that's you want the first half of WWR, but it will read W. What's the purpose of the third state?
Start popping.
Yeah, to map W to WR. And that way we can only transition to the final accepting state if we were able to pop everything off the stack that we were able to push. And we've read everything in the string.
The non-determinism comes in because we're testing every possible midpoint
Yeah,
at the same time.
yeah, the non-determinism, we know one thing about non-determinism is we can have two paths out of a state to consume the same character. So we're gonna do that. One of them will consume the character and add it to W, and one of them will teleport over to WR and start trying to remove that character. And then we have 2 threads running from that character. And then we see the next character, we have 2 more threads. Next character, another branching thread. This transition just pushes that bottom of stack character on, leading us to Q1, where some fun things are going to happen. What would we want to do from Q1 if we read an A? Push something to the stack that says that we read an A. So I think I can even draw these here. On an A, we're going to read the A. We pop nothing from the stack, and we're going to push, I don't know, we'll call it a 0, representing that there's an A on the stack. We can do the same thing for a B. We read a B. We want to pop nothing, and we want to push a 1 onto the stack. That gets us back to Q1. Well, we want to be able to transition from Q1 to Q2, where we're going to be doing the popping arbitrarily. How could we specify that in terms of this notation? Yeah,
You could have A or B in the input string. A or B transition, add nothing from the stack.
So what's not allowed are two transitions that consume the same character and make the same stack transition. But you can have two different transitions out of a state that consume the same character but do different things to the stack. That is allowed via the non-determinism. Yeah,
So we're like simultaneously pushing everything onto the stack and also trying to pop everything.
yeah. Think of it like you're forking threads. And now you're gonna have one thread that continues trying to add and one thread that's trying to say, is this the middle point? And let's say we have a 10-character string. The correct time to transition is after the 5th character. But we're going to be trying to do so after the 1st character, after the 2nd character, after the 3rd character, after the 4th character. All of those threads are eventually going to fail. We're also going to be trying to transition after the 6th character, and the 7th character, and the 8th character, and the 9th character. Only after the 10th character has been read, that one thread from the 5th character where we fork is going to succeed. And that's where we can stop.
So why does that transition have to consume a character? Because doesn't that mean that it would be an odd number of characters?
Yeah, no, you're right. We actually do want to pop if we consume this A and transition over, yeah, we actually will either want to be able to just generically do this, or this needs to be the first pop.
Yeah.
Yeah, so if it is the first pop, then we should take off A0. And we should take off A1. we back? Looks like we are. Excellent. All right. So. Any questions from remote? I know that when I cut out like that, you don't get the full concept of the description. How are we doing? Does everything make sense with regards to non-determinism, with regards to finding a single thread that accepts, so we accept the whole string? Yeah, sorry. So basically what we did is we came up with the NPDA. We started figuring out when do these threads branch. If they branch, then we continue forward with both branches or all branches. Sometimes those branches are going to reject, so they basically die and we don't consider them anymore. And eventually there is a single path here that leads to acceptance. And so that allows us to accept the entire string. So the second state here is doing all of the pushing. The third state is doing all of the popping. And we use non-determinism to match the string. Basically, is there a possible middle point? To do that, we're going to consider all possible middle points, but that's what we have to do, just consider all of the middle points. If there exists a single middle point that maps to WWR, then we accept. Questions on that? All right, let's see if we get exactly. That's the next slide that has the other solution, the slides solution to this. See if we got exactly that. We should. Here we go. So instead of drawing it out on the slide, I just gave a list of transitions. Questions on seeing the transitions defined as a triple leading to a tuple? I think on we go. So the next thing we might want to be able to do is come up with the intuition and logic for converting between a context-free grammar and a non-deterministic pushdown automata. How can we get a sense of how does the grammar rules that we've been making align with these states and transitions in a state machine? Just like with regular languages, for any context-free language, we know that there is some NPDA that accepts it, just like for any regular language, there was a DFA or an NFA that accepted it, in fact, many of them. So to be able to show and be able to prove that, we need to be able to come up with a process that converts a grammar into a state machine. And it turns out that this process is really easy if we use the other grammar normal form that we didn't talk about. So here's where we're going to come back and talk about Greibach normal form a little bit. To refresh you on Greibach normal form, there was the right-hand side of each production was a single terminal followed by one or more non-terminals. There's 0 or more non-terminals. So if we have a grammar, it's not in GNF, we need to convert it into GNF. Then we basically do a leftmost derivation of each production defining the transitions. What does that look like? Let's give you an example. Here is the entirety of a grammar. So we first need to convert this into GNF. I won't go through that process perfectly, But here is the result of converting this into GNF. We see a single terminal followed by 0 or more non-terminals in every production. We know that the grammar always has any string in the language that this grammar can produce, and that language the grammar represents starts at the starting state. Starts at the start symbol in the grammar and the starting state in the NPDA. So we can immediately push that symbol onto the stack that we use in the NPDA. So it defines this transition. From Q0, we make no change. We push the bottom of stack character onto the stack and transition to a new state, Q1. And now on top of that, we're putting the start non-terminal. So we're using the non-terminals in the stack. We're going to define transitions based on the single terminal that we see at the beginning of these productions. And then we're going to make changes to the stack based on the following non-terminals. So we now look and make a rule for each transition that we could make from the start non-terminal. So we could consume an A and have an S and an A on the stack, or we could just consume an A and be done. So that's going to involve two transitions. So this says, read an A from the input, pop an S from the stack, push SA. So you're going to read this character, pop this character, and push these characters. Or read this character, pop this character, push nothing. Nothing follows that A. So that defines two transitions out of the starting state.
Pushing S.
Yeah, so you're pushing two things. The A on the bottom and the S on top, because we need to resolve that S first. So it gives us this. From Q1, when we read an A, then we're going to pop an S, and we can either stay in Q1, push an SA, stay in Q1, push nothing. And that represents these two productions that have S as the left-hand side. Questions on that? Clarity? Everything make sense? It's okay if not. Continuing. When we see this production, capital A, arrow B, capital B, it says we're going to read a B, pop an A, push a B. We read the terminal in the GNF grammar. We're going to pop the left-hand side, and we're going to push all the non-terminals on the right-hand side to follow the terminal. Capital B, arrow B, just says we're going to read a B, pop a B, push nothing. So we have now a very easy algorithm to take a grammar in GNF and convert that into the transitions that make up an NPDA. So assuming, this is something I haven't shown or proven, that any grammar, any context-free grammar can be rewritten in GNF, then we have the ability to parse that GNF and easily make an NPDA based on that. You would just do this for every production in the grammar. We just need one last transition. If the stack is empty, transition to an acceptance state. And that won't be anywhere in the grammar, but it's something that you just have to add at the end of this process regardless. All you would have is that. Some notes about the process. You can utilize this state Q1 for everything involving parsing any sequence of characters. The only reason you would ever want to split these states is if the language is in a certain form that says there's a first half to something and a second half to something. So when do we transition from the first half to the second half? We just saw that as an example with the WWR. There's a transition from reading W to reading WR. All right, let's have you do one. First of all, grammar in GNF. First thing we should ask. It is in GNF. So let's go ahead and draw an NPDA that accepts this. Take a few minutes, either write a list of transitions or draw out an NPDA state machine. I'll put you on the right track by saying 3 states. Any questions? Trouble getting started? How many total transition rules we're going to have in this middle state? Should be 6. One for each possible production in the grammar. Something like this. We're just going to go production by production and say that From Q1, these are all gonna be from Q1 to Q1, there's no deviation from that across any of these. So from Q1 on an A, we pop an S and push a capital A. So on an A, pop an S, push a capital A, that's a rule. What are all of the rules here for consuming an A from this? We can say we go from Q1 to Q1. On an A, we pop an A because that's the left-hand side. We either push ABC, which are the non-terminals that follow, or the nothing. So we just pop the A and nothing else. We push nothing else. We could also, from A, derive the B capital B. So we'll say reading a B, popping the A, push a B. Similarly from B, all we do is read the B, push nothing after popping the B. And from a C, pop the C, push nothing. So direct mapping between the grammar productions and the middle state transitions. Yeah,
So because it's in B and F, I think I can generalize this to, you always pop the left side, you
Yeah.
push the non-terminals and you
Yeah.
read the.
read the terminal. Yep. Yep, that's the only rule. Just do that for every single production and that will define all of the transitions in that middle state. Done.
Does that mean that all of these only have like 3 or 4 states?
Most of them, yeah. There are times when you're gonna want to split states, but yeah, it's really, this is why visualizing NPDAs gets really difficult. As soon as the grammars grow beyond the toy grammars that we're using in class, if you're using a real grammar, then there are going to be possibly hundreds of transitions off of a single state. And that's just disgusting to even think about visualizing. So which is why we write it usually down in terms of the transition rules like this when we're dealing with complex context-free languages.
Is there online like a visualization of what the grammar would look like for like, say like validating like C or something?
Yeah, just look up the C grammar. That does exist.
Well, like, is there a visual of the actual?
Oh yeah, the actual,
Automata for that, or is it just so like complicated?
probably, maybe.
We'll look it up.
Yeah, I'd be curious as well. I'm familiar with visualizations for algorithms that we cover. So for instance, for those of you who didn't fully read the CYK assignment, there's a link in there to a visualizer where you can input a grammar, input a string, and watch CYK work step by step. I put that there so that people can check your work and make sure that your algorithm is step by step producing what is expected. So it should certainly help you in the debugging process, as well as it tells you which cells are being referenced for any given lookup that you're doing. So you can make sure that you're pulling from the right parts of the table that you've created. So visualizations like that are great and nice, but yeah, coming up with a grammar for syntax of a programming language certainly would have a very complicated NPDA. So there's, all that's left is that last transition to a final state. And we're good. Think. Yeah, no, we're not gonna do that yet. We're out of time for the day. We're gonna come back and handle going the other way tomorrow. That's where we're gonna start at least, saying we have an NPDA and we write a grammar for it. What are the rules for that? Then we'll transition into talking about deterministic pushdown automata and why we don't just start with those. Why are they a different language class than the NPDA?
Yeah, I couldn't find anything.
Sorry?
I couldn't find anything.
Yeah, it's pretty gross. At any particular state in the syntax, let's say you have something like variable equals, what's the next thing that could show up?
Yeah, also, I mean, there's not really a point to make an NPDA that we're seeing, like, that really.
Yeah.
So it just feels like essential.
Yeah. All right, I have office hours starting now. If anyone has questions on anything from class, from the homework, or anything else. No, I'll see you tomorrow.